So let's continue our examples where we're looking at angular momentum and its conservation. I've got three more examples here. They're a little quicker than the previous one, but it's important again to understand when angular momentum is conserved, and when it is conserved we generally look at a change in angular velocity. So the first one I alluded to earlier, we have a diver. Diver starts in a pike position and then tucks, and they start spinning faster and faster. So we can look at how much faster they're going to rotate based on how they change their angular momentum, because they change the shape of their body. So in the information, we reduce the moment of inertia by a factor of 3.5. And you can kind of understand it. When you're extended along here, and let's say your center of mass there, you've got a lot of mass out beyond your center of mass. And when you tuck in your center of mass there, the R part is reduced. Okay, how to calculate that? It's pretty complicated because the body is not a nice regular shape. So that's where the 3.5 comes from. So basically what we can say is I prime over I, the initial, is 3.5. I'm sorry, I gotta reverse that because we reduced it. So I divided by I prime is 3.5. Okay, we'll come back to that. So if the diver makes 2 rotations in 1.5 seconds when in tuck position, what's going to be his angular speed in revolutions per second? So we don't have to mess with radians here, but you could. It would give you the same ratio when we go into tuck position. So before we can answer that, we got to ask ourselves, well, what's our guiding principle here? Well, the guiding principle is angular momentum and its conservation. There is no conservation of linear momentum because the diver's falling. There's an external force, gravity. Now with the question about angular momentum, we ask, is there an external torque to the system? Well, the torque is not coming from gravity. So gravity is certainly a force, but it's not exerting a torque on the person. The person gave themselves an initial torque when they pushed off the diving board. That's what set him or her in spinning. Okay, but once they're in the air, there is no external torque, even though there's an external force. So long story short, we can say sigma L equals sigma L prime. And that translates to I omega equals I prime omega prime. Okay, so there is no MVR here because we don't have an object moving linearly colliding off center, so to speak. So this is pretty straightforward. So I can say omega prime, our new omega, over our original omega, which is really what we're interested in, is going to be equal to I over I prime, which we already established is 3.5. So if the original one's 2.5 rotations in 1.5 seconds, which is an odd way of putting it, but I guess it is, that's 1.33 rotations per second, or revolutions per second. I'm going to translate that to revolutions. So if I want the new omega, that's simply going to be 3.5. That's an amount of change multiplied by 1.33. Okay, giving us, wait a second. Yeah, so I'm not sure what that gives us. Someone did the math wrong here, but you can work that out. All right. All right, let's continue on. So, similar problem, but again, not so obvious as to why it's similar. So imagine we have a disc, a potter's wheel, that's rotating about this central axis. We're looking on edge. Okay, so it's going around with the angular frequency, or omega. So we'll just call that omega now, in revolutions per second. Okay, it's a solid disc. That's going to become important later, with a certain mass and a certain R. And then it drops a spherical chunk of something. In this case, it's a cat, from the axis of rotation. So it's dropped offward, some distance R from there. Okay? And the cat digs in its claws so it doesn't go flying off and goes round and round and round. So we can then ask, what's the angular speed of the wheel, right? That's omega prime, once the cat has fallen on there. Okay, so let's figure out, why would it change at all, if at all? So when we drop the cat from above, that's assumed there, okay, when it hits, it exerts a force, and since it's off an R, Okay, you might argue, well, then it's exerting a torque on it. And it kind of is, but if we include the cat as part of our system, and not just the potter's wheel, then we can say that torque is an internal torque. And so since there's no external torque, then we know that angular momentum is conserved. And that's really what we want to do here. We want to say sigma L equals sigma L prime. Now it's just an issue of how do we calculate each one. Again, we're going to use the I omega part, but we want to look at what the I's are, okay? So in the first case, we just had, before the collision, it was just the solid disk of the potter's wheel. So that's 1/2 mr squared. Whoops. And we're going to multiply that by whatever omega the potter wheel had. We have it 1.5 revolutions per second. I'm just going to leave it as omega right now. Now, afterwards, the cat is on here, so the cat's going to change the moment because that's a lump of mass. And kind of like a problem we did with the stick prior, we have two terms in our new I. Okay, so our I prime is going to be still the 1/2 mr squared from the potter's wheel, the disc itself, right? That hasn't changed. But now we've got a new mass, the mass of the cat, some distance away, so I'm going to call that little r squared, away from the center, right? So if this is little r and the radius of the potter's wheel is big R, let me make that clear, times omega prime. Okay, so I'm not going to go ahead and solve that here because that's going to take more time than I really want to put in there, but you can work out the numbers because we are given big R, we are given the mass of the cat, we are given how far away it lands, it's little r, and the mass of the wheel. So I'll let you work that out. It should be pretty straightforward. If you do it right, I'll give you an answer. In terms of revolutions per second, omega prime, you should come out to be 0.47 revolutions per second. And as expected, that's less than what we started with because we've added a bigger moment without changing the angular momentum. Okay, let's do the last problem, which is the least involved of them. So we want to understand graphs. So I've got the first graph, I have angular velocity as a function of time. And we are told that the object, whatever it is, has some moment of inertia I. So two questions. How could we use the graph and given information determine the following? Angular momentum at any time. Okay, so we want to find, that's L, the connection between that and omega. Well, that's pretty straightforward. L is I omega. We're given I, so we would just read the omega at any given time. Okay, it's as simple as that. So if I want to know what's the angular momentum here, I would read what the omega is multiplied by the moment. The actual time itself is irrelevant. So this implies that since L is changing with time, because omega is changing with time, angular momentum is not conserved here. Okay, how would we go about finding the net torque acting on the object? Ooh, that's a little less obvious. So connections, torque, angular velocity, angular momentum, anything we know about that. And if you go back to the front page, we saw that all right, so I got interrupted. I forgot what my train of thought was, but I'm going to pick up right here. So we're trying to find net torque. We're trying to relate it to angular velocity and time. And we had an equation on the front that did something with that. And basically it was the idea of impulse, that a torque times a time equals a change in angular momentum. Okay, so we got torque and time in there. Where do we get angular velocity? Well, angular momentum is I omega. So now we see the connection. So the net torque, if we solve it, is omega over t times I, and I want you to recognize omega over t, or the change of omega over t, as the slope. So the torque in this is nothing more than the slope of this graph multiplied by the given angular, or moment of inertia. All right, last problem. Now we're given same object, but now we're given its angular acceleration as a function of time. And how would change in momentum at any time be determined from the graph? So we want not L, but delta L. So this should be pretty straightforward in that delta L is going to equal tau times time, right? There's that impulse idea once again. So how do we get tau from that? Well, that's just I times alpha times t. So we don't do anything with the slope, all right? Actually, I take that back. What we want to do is we see that we want to do the area under the graph because the alpha is changing with time. We got to take that into account. So let me reiterate that. That's going to be I times the area under the graph. Okay. Or another way of putting that, the area under the graph is nothing more than alpha times the tau, which is omega. So we get I times omega. Okay, that concludes our long introduction to angular momentum.